Morning, everyone. Thanks for coming out. We're going to give people a few more minutes to sign in and get logged in and all that, and then we'll get started.
Hey, Anthony, can you hear me?
Yeah, we can hear you.
Okay, great.
Wait a few more minutes, and then we'll get started. Hey, Ferry, this is Anthony. We're going to get started in a few minutes until folks sign in because we still have people trickling in. Give us a little longer. All right, let's get started. Morning, everyone. Thanks for coming out today and joining us on our webinar as we hear from Wes and Kenneth from Tasq about their tools and how they're sort of making everyday lives easier for the guys on the production side. I definitely wish I had something like this to help me prioritize my day. I'm from the SP Print-Based and Data Analytics Study Group, the co-founders, and we're just here to start bringing you events like this, and also when things get back to normal in the Midland area, do sort of some more in-person events and socials and whatnot. Stay tuned to our LinkedIn page and Facebook, website, and all that. More updates. We have another event coming up in June, so stay tuned to our social media for details on that. And I'm going to hand it off to Wes Hamer from Tasq to sort of talk about his company. Thank you, Wes.
Yeah, absolutely. Thank you, guys. Hey, everybody. Welcome to the presentation. My name is Wes Hamer, one of the co-founders of Tasq. On the line, you've got Kenny Wynn, the other co-founder of Tasq. We'll run through the presentation, probably take about 45 minutes or so. Intermixed in there will be a demo that we'll run through as well. And any questions you guys have, ask away at the end, and we'll address the questions at the end of the presentation. So just talking about a little bit of an overview. If you can move to slide 2, Kenny. So a little bit of the agenda. So we'll go over an overview of Tasq as a company. What is Tasq? What are we doing? We'll go into the demo right after that. And so spend a little bit of time not going into all the details there, but kind of a overview and summary of what we're doing. We'll then dive into some of the use cases. So specifically, if you look at some of the predictions and some of the modeling that we're doing, how are we actually doing that with specific different artificial lift or different types of data. Then we'll go into a little bit of our data science framework. So I think it's helpful, especially with everybody on the call, to talk about not just talking about predictions and modeling, but talking about framework architecture, where you can go wrong, and what you need to design around, which kind of leads into the last point, is going to product design and machine learning. So I think this is an important topic that is less talked about in industry, and specifically with machine learning, how do you build a product to gather feedback from to enhance the models over time. And so there's a good amount of product design and user experience that goes into that we will touch on as well. All right, so a little bit of an overview of Tasq. We've come from production operations, and really we believe that it shouldn't be as hard as it is today. If you think about production operations and production going up and down on a daily basis, really you have production dip 2%, 5%, 10%, some amount on a daily basis, and it almost seems like Groundhog Day, where everybody in the organization is asking, why did production decrease and what are we doing about it, right? Those questions happen almost every day. And so the piece of that we're really trying to completely automate is that should be available at somebody's fingertips, right away. Not just talking about what wells are down and the volumes that they're down and what that is due to, but really talking about why. What are the failures? What are the reasons? Who is actioning what wells on a daily basis? So if you think about production operations, it's almost like daily chaos that is happening on a daily basis. And I would say about probably 4 hours out of everybody's day, that's across engineers, foremen, field techs, is spent either digging to try to find those issues, digging to try to find why, and then communicating across the organization who is doing what. I think that's a little bit archaic, and there's a better way to do that going forward. Really, I think that the main reason for that is you have data that is segmented across multiple systems. And so you have your SCADA data sitting in one spot, maybe you have your rod pump data in another spot, you have your spot fire reports somewhere else, you have your failure information somewhere else, you have the knowledge of the workers, and that's obviously in their minds. And so how can we really connect the organization in a better way by connecting these data sources in a better way to drive an efficient operation? And so really think about the utilization. I think that in production operations, you have all this data, but it's not really being used to drive a proactive operation. And so, which really leads me to my last point, is really not learning from operations. The failures that are happening right now, or the deferment, the down production, the downtime, however you want to categorize it, has happened before, right? It's happened last week. The failure types have happened maybe a year ago, whether it's scaling issues, whether it's downhole bridges, control valve issues, whatever the case might be. I think that most operations and most organizations are not set up to learn from their users and learn over time to where you're really accurate and moving to a completely predictive organization. So, in general, those are the problems that we are looking to tackle at Tasq. And so what is Tasq? So we are a task management system that integrates machine learning to connect operations. Really what we're doing is we're connecting machine learning with the assignment of tasks, and that's across different roles. So if you think about how the industry has traditionally been approached, it has been, there's a machine learning application or a specific artificial lift optimization, but that sits aside, right? That is kind of separate from the day-to-day operations and really integrated into what everybody does on a daily basis. We really believe that there is a huge benefit of integrating that into everybody's task list on a daily basis or workload, and engaging with machine learning, whether that is labeling data, whether that's predictive modeling, and so on, to really engage with the users and learn from the users. I think there's a lot of knowledge and there's a lot of intelligent people in the industry, but the systems aren't set up to connect data and learn off of the users. So another aspect is we're role-based, and so whether you are an engineer, a foreman, a field operator, a team lead, we have the application set up to be contextual to that user. So if I talk about how Tasq works, really this is a pretty high-level overview. And so, the first part is the SCADA data is plugged in. So we plug into your current SCADA system. We have no hardware. We really think that the existing data can be utilized in a better way, and we can create these labeling functions, and we can learn from these deferment signals, the failure signals within that high frequency data. And when I say high frequency, I mean anything from 1 minute to 30 minutes. So whatever you're currently pulling right now in the field. So we plug that data into our system. We have a suite of anomaly detection algorithms that detect abnormal behavior. Now this is harder done than said, because really, if you start looking at cyclical wells and different declines and different well types, different surface configurations, what is normal? And so that's something that we flag to the user, and sometimes whether that is known or unknown, whether the issue is a specific issue that Tasq is predicting, so whether that is a control valve failure type or whether it is a downhole ESP motor failure or whatever that case might be, we assign that to those users. If it's unknown, we also unsign it as unknown, and that would be the task would be to label that, so Tasq can learn from that signature going forward. So we have a way to assign work throughout the organization, and this is, you think about pump by exception, which I think as a term has been more popular over the past 5 to 10 years or so. Really with pump by exception, you are dismantling your routes, right? And so previously an operator or a team used to work within their 30 wells, 50 wells for the day, used to visit, for the most part, every one of them. Now moving to pump by exception, you're visiting the top wells that are down, or the 80-20 rule. Sorry for that. And then going forward, really, if you think about what we are doing at Tasq, really, I think to be really efficient within operations, you have to understand the failure types, and you have to include predictive behavior within that task list or within prioritizing your day. So that's what we're trying to do by assigning work out to everybody in operations. And then number 4, we seek user feedback. And then number 5, we go into predicting these failure types and failures to move to a proactive task list on a daily basis. So you think about how that looks like, the task way of operating and what is normally set up. I would say normally set up in current operations. Now, don't crucify me on this current operations. Your organization could look completely different than this. But in general, this is what we've seen across the industry, is that there's this pretty rudimentary way, and a lot of time is spent trying to dig down and find out what's real. And really, the problem here is that you have all this production decreasing and increasing on a daily basis. Some of it's due to allocation issues, some of it's due to automation issues, some of it's due to true production loss, some of it is about to fail. So really, if you take all of that and filter out the noise in the system, really that's what we are doing, but being contextual on what the issue is, and then making recommendations for the users. And so what we're trying to do is connect every piece of this process, because really when you connect every piece of this process, through reporting the data, through labeling the data, through understanding what everybody's doing on a daily basis, through prioritizing people's day in a certain way, I think that you really achieve an efficient organization and operation when that happens. And next slide. And so what we are doing, if you see on the left-hand side, we are taking the different data types in and we're contextualizing it to a specific task. You know, whether that is deferment, whether we're predicting out cycles, whether we are understanding the behavior of high line pressure or running a predictive model on certain artificial lift types. We contextualize that to the end user. So that user is set up with a list. We have either recommendations or we are peeling a layer off on what the exact issue is. And that can be across the field tech, that can be across the engineer, foreman, and a team. We'll dive into a demo here in just a minute so you can actually see some of these features and functionalities. But that is, in essence, what we're doing at Tasq. And so in summary of the overview section, everybody, we believe in a better way. You know, I think in production operations, we've been accustomed to lethargic systems and kind of passing spreadsheets back and forth. But, you know, we really believe at Tasq connecting a lot of these pieces of the puzzle and building a learning system. So really a system where you can label data appropriately. That data can be used to feed back into a model. That model can be used to drive a proactive and a predictive task to individuals across all failure types. And so we're not just specific to rod pumps, we're not specific to ESPs, plungers, or whatever the case is. Really think that the framework of building a learning system enables every type of failure signature, every type of SCADA signature that you can see to learn off of that over time. And then the third piece is really, we just believe in a modern product. So a product that's well designed, that's intuitive, that's easy to use, that gives a good user experience. You know, I think I would assume most of you have seen open wells or WellView products, and I mean that just kind of kills me inside because it takes about 15 clicks to get to where you're going. It's slow, it's not intuitive. Everything is very rudimentary and form-based. And so really what we're trying to do is also build a application that you want to use, that you can get in on a daily basis and utilize and play around with as well. All right, so the next section, we'll go through a little bit of a demo. And so as Kenny, co-founder, is pulling up the demo, you know, we are broken up into 5 different categories within Tasq. So we have schedule, we have my tasks, we have operations, workflow, and analysis. We're going to start on the operations page. So really the operations page, you see a breakdown of the operation as today. So you see production and deferment. So we're putting out deferment as quote unquote lost production or downtime. That can be categorized many different ways. We have our own way that we'll talk about here in a second of how we are calculating quote unquote deferment. But really just your high level stats on production and deferment for the day. Below that second section, really you see out of all the lost production, out of all the decrease in production, the deferred volumes for the day, how much is being worked on across what role? And so whether that is a field operator, automation, engineer, and optimizer, and so on and so on. And so really that is an output of the assignments that we're doing in the system. And so you can kind of get a high level overview of those numbers and how they are increasing or decreasing as the day goes on. The next section is top deferment. So this is an output of some of the classification that we're doing. So you can see your top wells that are down for the day. You know, really, I think the important thing that I believe production operations and most operations are not good at is really contextualizing the data to the end user. So as you see here, we have the volume that's down, the volume that's deferred for the day, what the specific issue is. So this is an output of classification, some of the machine learning for the signals that we're doing. and specifying what the specific issue is. Obviously, how long it's been down for, that's not rocket science, and then who's it assigned to. But we really believe in contextualizing all this information. Instead of digging, it's right there for you. The second piece is top failures. And so what we're doing here is we're aggregating the failure types for the day. And this is also an output of machine learning, and trying to understand exactly what those issues are and what the volumes due to those issues are. Now, traditionally how this is done in oil and gas is you have down volumes for the day. Your operators go fill out the downtime today, and then you get the downtime report the next day. That's the cycle time and the lag that we're trying to bridge to be instantaneous. And so, I believe that to really be on top of production, you have to understand what the issue is due to right now, to be able to collaborate with and solve that issue. So it's either not a repetitive issue over time and it gets solved right away, or the right troubleshooting steps are assigned to that issue as it comes up. And then below that, we have planned work. And so this is any reoccurring work that's in the system, and you can kind of see the 5-day outlook of what's coming up. Maybe you can select, one of these, and you can swipe right on a work over handover and possibly delay that, or whatever the case might be. And so this is kind of an output of any upcoming work, and you have the functionality to swipe left or right, or to swipe, right on the gauges, on that gauge category for 14, and then you could delay that, and you can really interact with the upcoming work that you have in the system. And so if we move into, and real quick, I guess one other thing I forgot in this section, Kenny, if you scroll up, and apologies, we had a user error on my side, and so Kenny's having to go through the demo, and I'm talking through the demo. So if you go through to engineering and click on the engineering task per role, Kenny, you basically see a breakdown, and this is our demo environment. So the numbers don't exactly match up, but you see the status of those jobs for the day. And so these statuses are contextual per role. So for engineers, maybe your job types would be to label data, or your job types might be predictions, or your job types might be whatever the case might be. And you can basically drill down and see a live view of which jobs are complete, which jobs are labeled, which jobs are incomplete, and by who, and the well name and the tasks associated with them. So this is kind of an overview of what work is in the system and who is doing the work throughout the day. Obviously, as the day progresses, different jobs get reassigned and handed over to different people. So this is kind of a live view of what jobs are reassigned and the status of those jobs. All right, so if we go into My Tasks, this is a view of our task list. So these are the jobs in the system that we are assigning to the end users. They're broken up by, they're broken up by area, they can be broken up by role, but this is the intelligence of tasks coming into what should be done for the daily basis. You can see here that we have predictions, we have state changes, we have wells that are down, we have wells that are in failure mode. If you scroll down the list, there's jobs that we can label and jobs that are self-assigned. So intent here is we're really trying to bring all the jobs that are done on a daily basis, specify the task type. And so some tasks might be assigned to somebody as an unknown issue. And so they would ask for you to label what that issue is and to specify a time period. And that's how Tasq is learning from the system. But for example, I'll go up into the top of the task list and then click on the prediction, the second prediction here with the, So if we go down here, we see production, we have signals and well history here at the top of the page. You go on that 2-week view, you can actually see, So this is specific to an ESP. We're bringing the signals in here at a live view, and we're actually saying that this well is going to fail in 2 days. So this is how our predictive model is engaging with the user. And so you can look across each sensor. You can see the time period which we're specifying that it's most probably going to fail at. And you have a selection of what would you like to do at the bottom. And so you can either go to that, you can take action or wait and see. So if you wait and see, you can click wait and see and then submit. It actually locks that task. And so that task is locked on the list, and basically what we're doing there is gauging the effectiveness of a prediction. If you think about how predictions are, the accuracy of predictions, think about being predictive, running a predictive model in general. The question that we're trying to solve right here is, how do you know that your predictions are accurate? And then number two, how do you know what that accuracy is over time? And so the wait and see function is to do just that, is to benchmark if the predictions come true or if they don't. If a prediction does come true, you see the lock turn green on the top. And so that's a symbol of that prediction actually coming true. And so that's on your task list over the next few days until you unlock that. You can also swipe right on any job and reassign it. And also lock any job as well. So you can reassign it to a different colleague. It would show up on their list, that day right away. So it'd be real time. You can also delay a job. You can also snooze different jobs as well, and reject a job. And so we have these kind of different intuitive features and functions here to make it easy for the user to organize their list instead of scrolling and trying to find these wells on a daily basis. What we're doing here is we're also prioritizing the list. And so you think about predictions being at the top of the list, state changes. What we're saying is that there is a state change of the well. And so the well is experiencing some type of a downhole dynamic that Tasq is picking up. And so there's a change from previous state to current state. And then there's wells that are down, that are labeled, that are in failure mode. You can see that the volumes for state change, we have not highlighted, but we have grayed out text for the ones that we are less confident in. It's worth noting that some of the volumes associated with this, if you think about production operations and really the problems there, a lot of the problems stem from understanding what volumes are allocated and true as of today, or as of live. And so usually the allocated volumes, depending on how the field is set up, is delayed. And so what we're doing right now is having a live snapshot, and we're actually predicting that this is the volume change due to that said issue. The gray is what Tasq is predicting is that volume change, but we're less confident on that volume change, versus the white text, which we are more confident on that volume change. Now, if we have real true production as of right now, we can plug that in as well. So there's many different ways that we can do this. We also have wells that are down, wells that need labeled, and wells that are failure. So if you click on one of the state change wells, you have the icon there that is reassigned, or the icon there that is due to a task type. But really here we're showing that there is a state change pre and post here. And we ask the question, is there a state change for this well during this time period? So if you go down to that, Kenny, we have the ability to feed back into Tasq. Yes, there was a state change, not sure or no. So this is how we're seeking feedback from the users on how to label these specific type of issues. And really that's feeding back into the predictive modeling and the modeling that we have set up in the system. If you go into a down well, Kenny. And so if you go to the bottom here, so what we're doing right here, go to troubleshooting steps. What we're doing right here is we have different feedback mechanisms for different task types. And so if it is a down well and the well is in currently about to fail, we have troubleshooting steps for that specific type of task. If it's in a failure mode, we ask different questions. Obviously, for every different task type, we're asking different questions from the user, and we're learning through each one of their responses. All right, so if we go back to my task list, at the top, you have 3 bars, and you also have my task, my team tasks, and then everybody's tasks. So if you go to my team tasks, you can see who that job is assigned to. So at the bottom, it says Susanna Story, or whoever that person is. And so you have the context of who is handling that task for the day. And so you have the ability to search through all wells and tasks in the system. Okay. There's a little bit, obviously more details for each one of these task types, especially labeling and failure and so on, but we will move on. So the next piece is workflow. And so we have the application set up to create rules for the user. So any type of rules that want to be created. So if as a user, if you see, if you want to go back, Kenny, as a user, if you want to, you can see the list of assignments that are currently set up in the system right now. So you can see specific logic or rules that are active or that are paused. And you actually can see what we're contextualizing for each one of those rules, the accuracy of those. And so if a lot of users are rejecting those task types, then we are transparent in feeding back what the accuracy of those are. So if those either need to be paused or edited. But basically, you as a user can create any logic that you want in the system. So if the failure type is RTU board and it's been down for 5 days, you can assign it to engineers or whatever type of assignment that you would want. If the standard deviation is 3 for casing pressure and tubing pressure is increasing at this rate for all rod pump wells or plunger wells, whatever the case might be, you can add that into the system, and that will create a criteria to assign that job to whoever is designated. We also have procedures at the top, and so you have the ability to go through the procedures. So those procedures can be linked, just like we showcase in my task list, dependent on the failure type. And so, for example, if you click on one of those procedures, you can see that you can create steps, and those steps can basically be edited or adding new steps. If you click on one of those steps, you can see how many times it's been done in the field, and you can edit those actions. And then if you scroll all the way down, you can actually see there's a log of changes for who has edited what steps and who has created that procedure and what that procedure applies to. So this is a way that you can easily create different forms and different ways of inputting different type of troubleshooting steps or different data types within the system. Okay, let's touch on schedule next. So schedule, the other 2 functions we will briefly touch on and then move on. The schedule piece is any type of scheduled work. You have a 2-week snapshot on kind of a Gantt chart view of upcoming work that's in the system. So if you click on the top of that, near that green bar, you can go maintenance tasks. Maybe that can be workover, wireline tasks. And so any type of schedule work you can see, your team can see that, and whatever views you'd want to incorporate there, you can basically see what rigs are on what wells and so on and so on. Projects are also there. And so if you scroll down to that 3rd project, Kenny, testing, you have the ability to, and go to that first phase. So yeah. To select to input any projects that are in the system. So really the intent here is to be pretty clear and transparent about what projects are going on, what the value of that, what the scope is. If you look at the 2nd phase, what wells are selected for that project, and then the 3rd phase, when they were implemented and what that uplift actually is. And so we're normalizing some of that data and proposing or providing the analysis, almost automating the analysis for the user. So it's clear and transparent about what projects are happening on what wells to what results. So it's a quick snapshot of the schedule page. The last page is the analysis piece. And so this is where we're aggregating a lot of the classification and the machine learning that we're doing. So this is almost an output. Think about entering downtime on a daily basis, which is very time consuming. What we're doing is we're taking machine learning from the failure types that are occurring in the system, and we're aggregating that into the analysis page. So really we're automating downtime reporting from at a system level. And so you can see that this is increasing or decreasing on a week over week or month over month basis. What we have tagged here is also the how correctly this is identified. So if the users are saying, no, this task type is wrong, or no, this failure type is wrong, we are displaying and very transparent on the accuracy of the system. And if that accuracy is increasing or decreasing. At the top, we also have the ability to upload production targets, so you can find out how many days or months you are above or below target to make sure that that is clear and transparent across the organization. All right, so that concludes the demo piece of the presentation. Kenny, if you want to go back to the presentation. So Penny is going to take it here and talk through the use cases and talk through the data science framework before we conclude with the product design.
Thanks, Wes. Yeah, so I'll run through a couple of use case of machine learning or data science to some problems that we've encountered out in the field. So one of the first ones I want to touch on, a common problem that we find across operators is trying to figure out what the should-be production is, or really, if you think the inverse of that, how much production did I lose for that day, or need to gain back to get to my should-be production. It seems like a trivial problem, but when you think about it, most people approach it with a decline curve solution, which may be fine in the long term, but for short-term kind of everyday noise, it can be pretty high variance, right? So what we're trying to do really is, given a day-to-day's production noise, right? Taking that into account, what is normal production and what isn't. So the first step of this is really identifying where you have anomalous time periods in your production. Taking these into account, flagging them out, and then imputing essentially those anomalous values. You're essentially trying to create a profile of what is normal production. And once you have that, then really it's just an exercise of determining what the production for a particular well is day to day, including some of the typical noise profiles for that. And from there, you can kind of back calculate a production loss or production deferment. This the value of this is really being able to prioritize or add a value to a particular action on a well, essentially to help you sort through the day. Another case study that we've done is with ESPs, in particular, seeing if we can predict out when we think a failure will occur. So with this particular data set, we were able to predict out about 14 days with a 0.75 AUC, which is an area in the curve. It's essentially a metric for a true positive versus false positive rate. Basically, you want to be as close as 1 as you can. A 0.5 is essentially just guessing. But we found that it's a fair score. It's not completely 100% accurate, but it gives good indication when there's a problem on the well. If we move to 3 days out, about right here, we actually find that it's about a 5% false positive rate, which is pretty low and what you want, right? For ESPs, generally if you don't catch them in the midst of failing or before failure, then the remedy could be in the hundreds of thousands, if not maybe even $1 million workover job. It's if it's a pretty tough workover. So another use case that we're implementing right now is rod pump state change, detecting state changes in rod pump signals. When I say signals, these would be like fluid load, min and max load, the percent fillage. So you can see here that we're taking the raw signal and we're doing some feature engineering with it. So we're trying to extract out some key indicators that will help us find these changes in the states. So in this case, we're pulling out a peaks balance, which is, you can think of this as the balance between the peaks and the troughs against the mean of the signal. The slope, just a rolling slope over time, as well as the variance of the signal difference. And so to try to take out any seasonalities or trends and really just trying to get the raw variance of that signal. And then from there, we're essentially applying a clustering algorithm to determine or really group like signal values together over a certain period of time. And what this essentially shows or reveals is when we're seeing shifts in the values of these engineered features, which then translate to changes in the state of the signal, whether it's increasing in variance or there's a slope change, or maybe the peaks of the signal are more numerous during a certain time period than the troughs. So, and the value case this leads to is really being able to first identify when we're seeing changes in the rod pump performance, and really leading to if that leads to a failure or downtime, then it's something that we're essentially building up that data set to try to predict. Another thing in development that we're doing is obtaining the pump cards of these rod pumps and labeling essentially the pump cards themselves and the certain features. What we're trying to get to really, if you think about the last slide, the time series data there, is really just a summary of the pump cards, right, or calculated or derived from pump cards. And so really trying to get as close to the source of the data. We're trying to feature engineer and label important indicators in the pump cards, and really being able to infer the next shape of the pump cards, the next few shapes, to then detect failure or detect abnormalities. And then finally, this is a simple use case for a plunger well, or really any cyclical well, is being able to forecast out the production cycles of that well. So you can imagine if you're trying to do some sort of production benchmarking on a cyclical well, it can be a little bit noisy if you just draw a straight line average to try to predict the performance of the well. In this case, what we're trying to do is understand when there's an abnormality in the cycles of the well. And so if you can pick up enough abnormal cycles that the well is experiencing, then that gives you such an early warning sign of there may be something happening with this well. So now we'll get into a very high level framework of how we're approaching these problems and how we're deploying these. It's very generalized, but please feel free to ask me any questions on any of the details. So if you were to break down a data science problem process, generally the first step is, once you've obtained the data, is to process and prep that data. Really, this is getting in, understanding the data a bit more. So making sure you're cleaning it, getting it into a machine learning ready form, possibly even doing some of the feature engineering. So finding those key indicators that you want the model to train on. Then once you have your data set, then it's really about selecting the appropriate model. Sometimes you don't care for interpretability, and you may go towards a more black box approach, such as a a neural net or some AI-driven model, and that's okay. But other times you may want to trade off that accuracy or performance for being able to interpret what the model is doing and understand what features are important or not important. So that's really up to, depending on what you're trying to solve in that problem. And then, of course, once you've deployed the model and you have your initial performance metrics to say it's good to go, it's really important to get feedback so that you can continuously improve the model. There's the saying that all models are wrong, some are useful. It's important to understand that the model that you put out for addressing a problem is probably not going to be 100% right. And so that requires some user feedback or end user input to then improve that model and essentially get it better. So more specifically, some considerations when you're going through this process, you want to make sure that the data set that you have is clean and scrubbed. Do some descriptive analysis around how many missing values there are. If there's, a column with constant zeros or a constant value, you may want to take that out. So just really understanding the data set, which kind of leads into the feature engineering portion of this, where you're trying to understand key features or key indicators leading up to maybe an event or what you're trying to train against. So this, again, is more in understanding the data set as a whole and trying to extract out any key indicators that you want the model to look for. And then, of course, in certain data sets, balance is an issue, right? So if you're trying to classify different signals with different classifications or different failure types, you want to make sure that those are all balanced, right? So if you're training against normal type signals and other failure signals, more often than not, your normal signals, you probably have a lot more of them than your failure signals. If you don't balance that correctly, then that can lead to the model just telling you everything should be normal because that gives you the highest performance, which is not really the intention, right? So balancing is pretty important to ensure that you get some realistic outcomes. And then once you're getting into the training of the model, some models have lots of parameters that you can tune to help improve performance. This only helps so much if you choose some parameters that are, good starting points. Really, it's all in I would say most of the performance lies in the data set, making sure that you have good data, clean data coming in, because garbage in, garbage out. So, and another thing to check for if you're training a model and checking the performance, if the results seem too good to be true, you should probably check for data leakage. This is when you're training, some of your test data gets mixed in or is found in your training data, and this can lead to false high accuracies or high performances. And then lastly, I just want to leave off, machine learning, AI, data science algorithms, these will do what we tell it to do, but not always what we intend it to do. A good example of this is, as I mentioned before, the state change case. So, the intention is to find when a well or it has this change in state, but that could happen even when the well's down and coming back normal. It will probably still detect that state change, even though we may not care for that or want to flag for that. So just something to keep in mind. It's a continuous process to get a model to do what we intend it to do. So this is also kind of a high-level view of what I talked about. Really, the key takeaway from this is, even though I talked a lot about data preparation and training and the feedback of that the results. What's really important here is the architecture. So these processes that you set up for data preparation, for the model deployment, the feedback, the architecture is pretty important in terms of how you are going to finalize or put it into a production environment. This could include your real-time needs. Does it really need to be real-time, or can you have some sort of delay in your model inferencing? The data cleaning, how long does this actually take? Does it need to be optimized? Do you want to on-premise, or do you want to put it in the cloud? There's a myriad of different ways to design the architecture, but it is also pretty important and something to think about as you're going through this process.
All right, so next session, we're going to take a look into product design and machine learning. So how different problem sets are being tackled by design. So I'll kind of take a 100,000 foot view. So really going outside oil and gas, if that's what 100,000 foot view means, and going through some examples. So I don't know if anybody knows about Netflix, but Netflix contextualizes the screen image of a show based off of what you have previously watched and liked. And so if you are into scary movies, it will give you a scary screenshot of that with, Stranger Things being an example. If you're into non-scary things, it will have a non-threatening screenshot of that to be able to select on. So it's contextual, and it's contextual to the user. Zendesk is another example of where they actually predict a satisfaction score for the person or the user, and then the user has the ability to correct that. So that's how they're doing some of their machine learning on user satisfaction. And then the classic and normal examples of Siri and Assist. But the interesting thing to note between the two is Siri assumes that you can ask any question, but obviously, as most of you guys have done, it's somewhat frustrating when the question is not answered correctly. Whereas Assist, you think about this from a very simple standpoint, they're very, very clear on what they can or can't do, right? So they're asking, what do you want to do today, or whatever the question is, and you have the ability to select, and then you drill down from there. And so I think it's important to really take lessons from external technology and how we engage with users, engage with models, engage with machine learning. So the next slide really will show what we're trying to design around at Tasq. I think there's three big points here: explainability, feedback, and value. Really, explainability, I think, is what the industry has done a poor job at in general. I think a good amount of solutions have been pretty black box solutions, where if you have a prediction, if you have a model, if you have a set point optimization, whatever, you're not really understanding why decisions are being made. I think that can be very frustrating for the user, and really where I've seen it is that's where technology fails in implementation, specifically in the field, is lack of clarity and lack of transparency about why the model is making a certain behavior, or a certain decision, or a certain prediction. And so really, we're trying to design around bridging that understanding between the user and the model. The second piece is feedback. And so you think about models, and no model is going to be 100% accurate, or have a very high AUC. And so really you need to design around failure. And so design around the model being wrong. Because if you don't, the users will be very frustrated if there's not the ability to correct that and to feed it back into the model so the model improves over time. And so designing around feedback and making sure that those inputs are there and you're communicating with the users with clear, concise questions, I think is very important, and what we strive to do. And then also value, so aligning the goals of the results of the model with progress. And so, very unlikely that you're going to hit it right off the mark. There's always going to be issues. If you think about even a use case for artificial lift optimization, and maybe ESP failures or rod pump performance, whatever the case might be, there's other issues that happen, right? Maybe that there's a surface, maybe there's a power failure, maybe there's a third-party issue. And so we have to be open about how we take that in to incorporate into the model, and then how that is engaged with the users. Really, the intent of Tasq and for us is to ensure that there's progress over time. And so you're not starting out at 100%, you're starting out at some value and hoping to increase that over time. So there's a few aspects of how we're incorporating this in the product. We went over some of them before, but I'll point them out here. So Ken, if you could start that one on the bottom left. So the bottom left, we're showing prediction with the ability to specify a time period in the future. So this is showing the user what is coming up, and like we said, we're benchmarking the results. And so we're actually challenging almost the user to say, hey, let's wait and see if this comes true or not. And we have the top left, the prediction as well. The video on the top left, the yes right there. The ability to lock these tasks. And so this is some of the user experience and engaging if that will come true or not. The second piece is correcting the model. So if task did not specifically identify the state change correctly, you can correct the time period with a specific 10:11 a.m. or so. So that is feeding back into the model where we got the time period wrong. And then the third instance is transparency in the system. So if you play that video, then we're showing the accuracy of each one of the classification and the failure types that we are predicting out. So really, this is how we're approaching user experience within machine learning, because we think it's very important to have this engagement with the user. All right, the last slide, everybody. So these are some questions that we're kind of proposing that everybody think about. If you're talking about most organizations want to move to some type of machine learning, some type of quote unquote, I will quote unquote AI, or some type of predictions. But when you really start getting into the nitty gritty of it, how is it supposed to be tracked? I think it's a question that is a user experience question, and not so much a machine learning question. The second piece, how is your data currently being labeled? Are your inputs feeding into a model that is improving over time? Is that transparent to the end user? And then third question, is the operations platform that everybody is using, is that frustrating users, or is that gaining users' trust? So is the user experience very intuitive? Are the models transparent and trended over time? And are the users trusting that, or are the users just getting frustrated by the lack of transparency? So that concludes the user experience and the product design. Again, if you could jump to 27 right there. And so we will enter any questions that everybody has. Right.
All right, thanks, guys. All right, thanks, guys. Thanks, Kenneth, and thank you, Wes, for that great presentation. My name's Ronnie. I will be emceeing the question and answer portion. You're welcome to either type your questions in the question panel, or you can just raise your hand, and I will kind of cycle through back and forth those that have raised their hand to verbally ask a question, and those that have typed their questions in. Okay, so let's begin first with the type questions. This one was asked early on, so it may have been actually answered in the presentation, but I'll go ahead and ask it again. Would you call Tasq's platform that you demonstrated a business intelligence platform, and how does the term machine learning fit into it?
I don't know if I would, well, it depends on what the classification of the type of platform or the diversity that you have there, meaning, how are you quantifying other applications? I would say sure, business intelligence. I mean, I would say in general, what we're doing at Tasq is really trying to combine the management of work and the management of jobs throughout the system, but do that in a more intelligent way than it's being done right now. So, for example, instead of just taking everybody's route and saying, here's your volumes top down and your other work that's in the system, we're applying predictive models and machine learning into the engagement there. So you have the ability to label these different time series and integrate predictive modeling into different types of failures. And so really kind of pulling that all into one spot.
Okay, thank you. Let's see. Does the user have to manually specify what type of artificial lift each well is on, or will the program detect and classify these automatically?
Yeah, we will classify automatically. As you saw through some of the demo, the specific failure types or the specific predictions had different signal types. So those signal types are automatically picked up by Tasq, and then the models are applied based off of those signals.
Okay. And the next one, since ESP failures can be quite random sometimes, for example, equipment being struck by lightning, are there any types of failures that are particularly easier to predict? Are you able to predict remaining operating time?
Sorry, Ronnie, what was that last bit of that question? Are you able to what?
Predict remaining operating time?
Got it.
Yes. So I would say definitely certain failures are a lot easier to predict because they're a little more gradual in their indicators. Scaling is a good example of this. You can definitely see this increase in temperature over a number of days. That is definitely something a little bit easier to indicate whether a failure is going to occur. Now, with regards to remaining operating time, that does depend a lot on kind of the data set, right? So if you have a good sample of kind of time to failure, then from that you can derive kind of these time to failure or remaining operating time probabilistic curves that kind of give you an idea of, for this particular well in this particular state, how much time do I have left to operate?
Yeah, and I'd also say to that, Ronnie, we cannot predict lightning strikes. That's for sure. That's for sure. But no, I think that we've seen ESP data sets. Some of them are you have these power failures, right? I think that the question is, we're not so much predicting the power failures, we're more so predicting the impact that the power failures have on the overall failure of the well. So whether that is a motor shaft failure, whether it is sec tubing or whatever the case is, the indicators are actually different, and the model is built off of detecting that specific failure downhole.
All right, awesome. Now we have a hand raised. We'll go ahead and go to a verbal question. And I am sorry, I'm probably going to brutalize your name. Abubakar? I don't know how you say your last name, but I'll let you go ahead and ask your question.
Hello, can you guys hear me?
Yep.
Yeah, my question or my concern is how can you, is there a possibility to model your system in the future whereby it can work directly with a company-owned database like DSS WellView, whereby if you already know what your model, if you figure out what you can do with your model, like let's say take Chevron, I see some Chevron well, for example, you know what Chevron needs, so the system that the Chevron production engineers use, can you set up something in your model where their data can go raw from their system into your software, and they get real-time answer to update what they're doing?
Yep. Yeah.
Yeah, I think one of the challenges in this industry has always been integration, right? Integrating with different companies, making sure everything's set up. I think our hope is at some point in the future it'd be just a plug and play. We take in data, we understand the structure, and it automatically spits back out the analytics. I think it's just a matter of time before we kind of get into that kind of a universal, if you will, integration with everyone. But I think right now it's, every company has things set up sometimes very differently. So it does take some time to integrate.
Yes, and I would say to that, but yes, I mean, any feeds that are currently being used, we can basically take that data, and then you have the real-time ability to view that within the application.
Okay, thank you.
Okay. Next question. Is there an option in Tasq for user to download, import the live data into Excel or other platform to do further analysis?
Yeah, so any data that we're collecting in Tasq, you have access to. So we've set up an API that, well, depending on how you want to engage with that data, whether that is hitting the existing database that we have, or an API, or downloading it via CSV. Either way, pretty open to sharing that and making sure that that is transparent across the both companies, so that data is available for access.
Cool, great. Next question. How do you input the data that needs to be labeled in the app? Is it done automatically, or someone else has to do it through the app?
Yeah, so I would start this question by, there's some known failure types. There's some known models that we have. There's also some unknown failure types, right? So if a site is set up and there's an issue, downstream of XYZ valve, whatever the case might be, some of those failure signatures or those data signatures coming over will be unknown. And so, like you see here in the bottom part of the snapshot of the application, we have a specific label job. And so what we're saying as Tasq, as we don't know the type of issue here, can you label what that type is? And we think that it's round about this day, but can you specify the time? So that's how we are approaching data labeling. There's always going to be some unknown data signatures to start with. So the intent is, again, going back to the expectations, and the intent of Tasq is really progressing that accuracy over time, where we can peel back the layers on what the failure type is and predicting that failure over time. We do start out with the models applying that right away, right? And so we'll start off with some predictions, some state changes, some failures, some classification right away. But the user would, anything that we are designated as unknown, we would ask feedback from the user with a specific task as seen.
Okay. And I guess some follow-up. Go ahead. I'm sorry.
Sorry, Ronnie.
No, go ahead.
One other piece to that, I think that that's a key aspect of machine learning. I think the expectation of most people is that, wow, you're doing machine learning or you're doing modeling or prediction, so everything has to be accurate. But the reality is that's not the case. And so I would ask anybody who's doing that what the AUC is and what that is over time, what the false positive rate is, because I think that really dives into how you can improve the model over time. And a key aspect of improving the model is getting this feedback loop up and running, where the model is productionalized and it continues to feed back and it continues to become more accurate.
Okay, and a couple other questions. How many labels do you choose for your system, and are they separated by categories like failure, prediction, and so forth?
How many labels do we use? Yeah, so labels as in, I'll say the colors stated here. Would that be correct? Maybe because this is a typing question you don't know, Ronnie, so I'm putting you on the spot, but I'll take this one myself, and if it's not right, just type it in. Yeah, so we have these different types of labels. So we have failure, prediction, state change. We have a label as well. We have down. And so those are the specific type of issues. Within those issues, there's the type of issue. So for a state change, it could be a state change due to traveling valve leaking. For prediction, it could be a prediction for a specific failure type, for a motor shaft failure. For a failure, it could be a specific type of failure, hole in tubing. So we display that within the task card. And so if you click into that, you should be able to see that specific type of issue, and whether that is troubleshooting steps behind it or whether it's a specific series of labeling that's pretty customized to the user, as we showed in workflow. So you can set those tags up or that data up, and that feedback labels however you would want.
Okay. And what type of machine learning algorithm, supervised, unsupervised, reinforcement, or deep learning, are you using to make the predictions? And what was your training data based on? And what programming languages did you use to build the app?
Nice. I like that question.
Yeah. So I guess this is a multi-answer question. So I'll start with the language. It's the easy one. I primarily use Python, just because it's a pretty versatile language, particularly once you've built the model and trying to put it into a production environment. It just integrates very nicely with some of the other frameworks out there. R is a very popular one. It's very good for data science as well. It takes a little bit more work to kind of productionalize it, but it's still viable and commercially used. Those two languages I would recommend definitely for data science and machine learning. With regards to the models that we use, it's a range of them. So anywhere from just even simple linear regression, just to kind of initially understand the data set, to maybe XGBoost or random forest if we want to get a little bit more into the machine learning side, yet still maintain or retain that interpretability, down to neural nets, particularly LSTM neural nets, which do fairly well with time series data. That is, takes a little bit more work to kind of fine tune. You lose a bit of the interpretability, but as a kind of generalized model, you can apply it to a lot of problems. So, and then what was I think there's a third part to that.
I think language used in the application. So we have,
yeah, you said Python, and then what was your training data based on? I guess for this, for developing the app, I would believe.
Yeah. So the training data, of course, comes from some of our clients. The types of data usually are time series data. So generally the signals that you normally capture, whether it's on a rod pump well or just normally flowing well. So we try to capture the pressure data, casing, tubing, line, production data if you have it at a granular level. But for example, rod pump is peak load, min loads, pump fillage, food loads. I'm sure there's a couple I'm forgetting. ESPs would be generally what I think is normally captured, intake pressures, dry frequencies, amperages, etc. So a lot of time series data, but we also try to incorporate in any sort of, I guess I would call discrete event data. So if there's any sort of failure reports or any sort of notes, if you will, we'll try to structurize that to incorporate it in with the time series data.
Yeah, and the training set we had was about 500 million rows of data, so span back a good amount of failures. I mean, it's important to have a diverse failure set as well. So
that totally makes sense. That's awesome. All right, I've got another live verbal question from Jim Browning. Jim?
Hi. Yeah, I was wondering, I noticed that it seems like your presentation is very oil focused, and I had a couple quick questions that are primarily related to the impacts of it being a gas well or constrained by gas production. Do you, as part of this, one of the things that's a particular issue with gas wells or high volume wells, high gas volume impacted wells, are the impacts of gas contracts. with especially interruptible contracts. What I was wondering is, there are times where your gas production or even your oil production relates to market controls on your rate. So I was wondering if you've brought sort of that concept into the analysis so far yet.
Sorry, and this is Jim, correct?
Yes.
Hey Jim, could I repeat this back to you and
Yes.
Please correct me. Just want to make sure that we hit this on. For number one, I'll say yeah, for gas wells, you know, it's an easy switch, right? It just depends on what company wants and what's the benchmark of that company. Is it BOE? Is it gas? Is it MMCF or barrels? Yes, we can absolutely take gas specific data, you know, whether that is more gaslit field or plunger field, as we kind of showed for one of the use cases. The question specifically, if I could repeat this back to you, is using some of the inferences for gas and oil relationship or LGRs, and how is that constructed into the model? Is that correct? Or
no, what I was wondering is there one of the things that's common in a well that's constrained, its operations constrained by the gas contract, is that with an interruptible gas contract, you may have to constrain the production.
Got it.
Of that well. And it can be cyclic on a daily basis. It can be cyclic on a seasonal basis.
Yep.
And the thing is, not only does that have an impact on today's productivity, but it can cause other mechanical or reservoir issues. So what I was wondering is how you are on, you know, pulling that into it, or is that do you consider that a very location specific configuration?
I would say I'll kind of speak generally, and then Kenny can add on to it. You know, I would just say that is a input into the model, right? So whatever the constraints are in the system, it can be included into the modeling. Now, if there's other effects, you know, whether that is line pressure, whether it's you know, the decline on other wells in the area, or you know, whatever impact pressure could have, these are all you know, tertiary effects of some of that issue. But you know, we haven't specifically incorporated that, Jim, but it's not to say that that couldn't be something to incorporate.
And the reason why I was thinking about it is there's many, if not most, especially on smaller well contracts, are very interruptible. And the thing is that the amount that you shut in may not, or the amount you constrain may not be so much as a structured input, so much as a daily impact or not. And so it can be more of a interrupter event based issue, if that makes sense, because it's external and you don't always know what the market's doing. You have general ideas you don't know.
Yeah, and you know, I would say, you know, for the most part, you know, that's of course to predict that may be a little bit difficult, but I think it all comes down to the data that you're collecting and you know, essentially the problem you're trying to solve with that data. There's always going to be a limitation or extent to what you can infer from the given data set until you gain new insights and then add more to that data set to try to explain essentially the behavior, right? You know, the way I see really with any model is what you're trying to do is really trying to explain a predictable behavior, and a lot of times that means, you know, taking in all the information that you do have available now, and that may explain some, but those variances from that model is probably due to something that you're not collecting in terms of data that you may be needing to collect, right? So it's always that continuous search to find that new piece of data to then improve the predictability of the behavior.
Okay. Yeah, I see this. I've done quite a bit on in areas that were strongly impacted by gas markets, and here in the Permian Basin, this is an area that's going to growing area of concern. So that's what.
Yeah.
That, you know, that's what I was thinking of it. Well, thank
No,
you.
no joke. Yeah, absolutely.
All right, thanks, Jim. Okay, go on to the next question. What would be a recommended practice to get the data into your application? The application has a lot of functions and hence needs a lot of data. It also needs to be quality checked before. Is it common to have engineers that are only assigned to take care of the application?
No, you know, we handle that. If you mean take care of the application, ensure that there is, you know, data quality gaps and so on and so on. You know, the intent is that Tasq is doing that. You know, we've got different algorithms to understand comms errors or automation or data loss, and so on and so on. So we're doing a lot of work kind of behind the scenes to clean that up, to prepare the data so it's specific to us, you know, concise to a task. You know, we try to make that as hands-off for the users as possible. Like Kenny talked about for integration, there's many different ways to integrate. You know, integration is not specifically rocket science. You know, it's the data initially can be loaded by a dump, and so we can do it by any type of dump that you could export in, whether that is, you know, CSV or whether that is just a VPN or whatever the case might be. We can start from there and then move forward with live data after that. So that's kind of the two-step approach that we usually take is take existing historical data, load it into the application, run the models, and then move forward with live data after that.
All right. And we'll keep trying to go through. By the way, we may not be able to get to all the questions before the end of time, but we will have a copy of those and allow Kenneth and Wes some time to maybe get a hold of you, reach out to you, and answer your questions. So I'll go ahead and go on to the next one. It says, hi, how does Tasq discriminate well-operated data independently of an operator's total production? For example, wells in different reservoirs or basins may influence different failure modes and production problems compared to others. How is a Tasq framework designed to compare apples to apples, or does it aggregate all the wells into this model? That's the first question.
Yeah, it's a good question. You know, I think there's always going to be, and that's really the intent. I think that hits the head on some of the answers that I was trying to describe before. Really, if you think about, you know, machine learning, it's a framework, right? And we've built some models, and we built some predictive models and some state change models and failure models and so on. Maybe that completely takes away, you know, 70% of the issues right away from production, but maybe it's 50%, right? There's always going to be some area that we're going to have to learn off of. And so I would agree in general with the question as you move from basin to basin. You know, the framework is set up for Tasq, and really that's the intent, where we're capturing these anomalies, where we're saying that this is abnormal to what is quote unquote normal, and we flag that to the user to label, and then we learn from that response over time and then include that in the modeling. So I would say that is how the structure is set up. The structure is set up to learn from different, the ways different facilities, different wells, and different fields are set up. I didn't get the question on aggregating the total well performance.
Yeah, I think I could talk to that a little bit. So, you know, I would say our approach is maybe we may first deploy a model that is kind of a generalized model. But I would say the end goal is really to stratify those, say, producing reservoirs, right? If you have type A well and type B well, then really to separate those out model-wise, if you can. And if there's enough data, right? So a lot of times when you start stratifying the data, you start losing essentially your your sample count, which can influence the performance of the model. So sometimes it can be better to combine those data types, say, for this example, producing reservoirs together, because you may have a slightly better model performance, and sometimes it's better to split them out. But it's something on our end that we do. We try to evaluate the performance of the different combinations.
Okay.
And I'd say really quick, Ronnie, I'm thinking about a previous question that I should allude to as well. Somebody asked about kind of the steps of integration, and apologize, I'm tying on to the end of this question. One of the things about, integrating the data into the application is, it's a very kind of step-by-step approach, right? So we're not saying that we're going to include everything into this application all at once. I think what we've learned from previous clients is we start out by just simply having the functionality of task lists with a group of people and start using it, aggregating the metrics up, start showing the aggregated metrics up in operations and analysis, and start to expand the functionality of the application over time. So, this kind of a staged approach to implementation that we take.
Okay, great. And one other question from them. How long in your experience does it take Tasq to learn enough about well operations in a specific area, make good predictive failure assessments or production forecasts?
I'd say that you won't like this response, but it all depends. I think that getting up and running within 2 to 3 months is totally reasonable and what we've experienced before. So, but it completely depends if there's a whole slug of different facility types, data types, and so on and so on, and data streams that we're kind of combining, connecting, then that can be plus or minus, right?
Yeah, I would say that, even machine learning or the predictive models aside, there's a lot of just tools in the application to help manage the day-to-day operations, even without the predictive algorithms. It definitely compounds when you can get good predictions, and that typically depends on the data set, of course, coming in. So if you have some pretty granular data sets, pretty clean data sets, as well as good contrasting labels or century events in the data, then it can help, especially boost the model. Otherwise, there's always, once we deploy it, it may require user feedback to kind of get it up to speed, and that just depends on the existing data set.
All right, great. Thank you for all that. Again, I apologize about running out of time. We're getting pretty close. I do want to thank Kenneth and Wes for your great presentation and for all the discussion that followed. This was a really great Q&A as well. And I want to say that coming up on June 24th, we'll be having our next webinar. Please watch out for that. There will be a recording of this going out to all of you that attended. And it will be, you can also pay to download it as well if you did not attend the event. Also, we'll let you know that for those that didn't get their answers questioned or anyone else that would like to speak to Kenneth and Wes about Tasq, they can be reaching out to you later on.
Yeah, and Phil, last thing from us, everybody, appreciate everybody's time today. If you guys have any other questions, we can reach out to the existing questions, but if there are any questions or any thoughts or want to review in a little bit more detail on the demo or the data, feel free to reach out. Here's my email, here's my phone number. We can set up a secondary conversation and talk through everything.
All right, thanks guys. Thank you everyone for coming in.
Thanks everybody.
Thank you.